Hi everyone. In today's video, we are going to be looking at combination circuits. So a combination circuit is simply a circuit that has both parallel and series elements within it. And so to analyze that type of circuit, we need to remember everything about how to analyze series circuits and everything about how to analyze parallel circuits and apply those concepts to their respective parts. So here's a quick example of a parallel or a combination circuit. We can see that we have A and B, light bulbs A and B, are in parallel with each other. Parallel meaning that both ends of the light bulbs are connected to each other, and then that set of parallel light bulbs are in series with light bulb C and light bulb D. And so everything that we remember about parallel circuits will apply to light bulbs A and B, and then everything that we remember about series circuits will apply to light bulbs C and D, as well as A and B in series with C and D. And we'll see how that works shortly. So how we analyze these combined circuits? Well, let's take a look. The first thing that we are going to need to do is to find the equivalent resistance for any parallel branches within the circuit, and so that we can transform the combination circuit into a series circuit, or at least an equivalent circuit that is a series circuit. And then once we have a series circuit, we can do a circuit analysis like we are just analyzing a simple series circuit. So here's an example. Let's say that we have a circuit that has a 12-volt battery, we have a 2-ohm resistor, and then this little section here with two 4-ohm resistors in parallel with each other, and then a 6-ohm resistor on our path back to the battery. What we are going to do is we are going to, as we have in the first bullet point up here, we are going to find the equivalent resistance of the parallel branch. So this branch right here, the two 4-ohm resistors, we are going to figure out what the equivalent resistance of those are. So doing some quick math here, we can see that remembering what the equivalent resistance for parallel resistors are, it's going to be 1 over 4 ohms plus 1 over 4 ohms. And we take the inverse of that, and this gives us 2 ohms, which we can see here. And how I actually like to label that is because that was resistor 2 and resistor 3, I call that resistor 2, 3, not resistor 23. I guess if you end up having more than, 11 resistors, the numbering starts to get a little mixed up, but I call that resistor 2, 3 to know that it is a combination of resistors 2 and 3. Then my final step, which I like to do because it helps me to figure out what is the current in this whole circuit, is I like to further reduce that whole circuit into a circuit that has a single resistor, a single equivalent resistance. So this equivalent resistance, Req, it would be the combination of resistor 1, 2, 3, and 4. To do that, well, we can see here in this middle circuit diagram, we have 3 resistors in series with each other. So to find the combination, the sum of all of those resistances, we just add them together. So it's going to be 2 plus 6. We have 10 ohms of equivalent resistance here. So this is 10 ohms of resistance to this 12-volt battery. So that is how we are going to reduce the circuit down. And then in a fully fleshed out circuit analysis, you're going to be asked to find what is the voltage drop across each resistance, and what is the current through each resistor, as well as what is the total voltage, what is the total current, what is the total resistance, and then even what is the power, how much power is consumed by each of these circuit elements, and how much power is supplied by the battery. So in that case, then we have to remember, well, how does current work in series? And how does voltage work in series? How does current work in parallel? How does voltage work in parallel? And so we have a little table here that helps you to remember that in series, we have circuit elements that are in series. The currents are all the same. It means that the current flowing through the first element is equal to the current through the second element is equal to the current through the third element. All of the currents are the same in series. Whereas for voltage, the voltage that is supplied by the battery, by the time it gets all the way through that circuit, that voltage is going to be used by each of those circuit elements. The voltage supplied by the battery is equal to the voltage drops across each of the individual circuit elements, the loads on that circuit. And then for parallel, it's the inverse of that. For parallel, it means that the current flowing into a branch or the current that is flowing out of the battery is going to be split off into the different branches. Now that is a little more complicated when we have this combination circuit because it's not just the current out of the battery is going to be split off. Really, we think about it as the current flowing into a branch will be split off into the different branches. Whereas in terms of voltage drops across parallel circuit elements are all the same. And we'll see that shortly. Okay, so let's take a look at an example here. And here we have a setup that is looking similar to what we had before, just with slightly different numbers. So we have a 60 volt battery, a 5 ohm resistor in series with two 8 ohm resistors in parallel with each other, and then that is in series with a 6 ohm resistor. So what we are going to need to do is to take that parallel branch, turn it into an equivalent resistance so that we have a series circuit, and then we can even break that down further into a single equivalent resistance for the whole circuit, and with a goal of filling out a table that looks like this, where we figure out what is the voltage drop across each of the resistors, what is the current through them. We already have recorded down there the resistances. We'll end up figuring out the power consumed by each of them, as well as the total current in the circuit, the total resistance of the circuit, and the total power consumed or produced maybe by the batteries. So let's start with this guy right here. Let's start with our parallel branch there. To figure out what I'm going to call this resistance 2, 3, it's a combination of resistor 2 and resistor 3. They are in parallel with each other, so that's going to be 1 over 8 plus 1 over 8 to the negative 1 is going to be 4 ohms of resistance. So redrawing our circuit, it's always a good idea to redraw your circuit. We have R1 here is 5 ohms. We now have R23 is 4 ohms. And we have R4 is still 6 ohms with our 60 volt battery. And we can go one step further and combine this into a single resistance. So, and these are in series. So our equivalent resistance is going to be 5 ohms plus 4 ohms plus 6 ohms, which is 15 ohms. So our equivalent circuit, our most basic circuit here, is a 60 volt battery and a 15 ohm equivalent resistance. Okay, so now let's start figuring out what are the currents and the voltage drops across each of these elements. And the place we want to start is with this last circuit that we drew. So I'm going to actually show you here. What I've done here in PhET is I've created these circuits. I've created the initial circuit, and then I have reduced it down to a simple series circuit with the original 5 ohm and 6 ohm resistors and this 4 ohm equivalent resistance for resistors 2 and 3. And then I've even simplified it down further to the single resistor and the battery. And what we're going to do is we're going to use, starting with this circuit, use Ohm's law to figure out what is the current flowing in this circuit here. And we're going to see that the current flowing in this circuit is going to end up being the same as the current flowing in this circuit because these are both series circuits. Now, it's not going to quite be the same as the current flowing through this entire circuit because we have a parallel branch here, And when the current flows and hits this little junction here, it's going to split off. But what we will see is that the current that we find in each of these two equivalent circuits here, it's going to be the same as the current that flows everywhere else besides this parallel branch here. So let's use Ohm's law. And what we're going to find is that the total current, or the current flowing out of the battery, as it's maybe better referred to, it's going to be the voltage, the total voltage, or the voltage of the battery divided by the equivalent resistance of the circuit. So that's just Ohm's law. And so we have a 60 volt battery experiencing 15 ohms of resistance. So that means we are going to have 4 amps of current. And let's see if that's accurate here. Take our ammeter, stick it into the circuit here. We can see current's flowing pretty quickly, and it has 4 amps of current. And that 4 amps of current is everywhere in this because it's a simple series circuit. Now, is that the same as this circuit here? Well, in fact, yes, because this 60 volt battery is experiencing 5 plus 4 plus 6 ohms of resistance, 15 ohms of resistance. So it's 4 amps of current there, as well as here 4 amps because it's experiencing 5 ohms. And what's equivalent to 4 ohms and 6 ohms here as well. Okay, so back to our example. This 4 amps of current, that is flowing all the way through here. 4 amps flowing all through this circuit here. It's the same as the 4 amps flowing through here. And it's flowing over here in all these series elements, not through that parallel. The parallel one we're going to figure out shortly, but there's 4 amps flowing all the way through all of those other elements there. So what we can then say is that the total current is the same as the current through circuit element 1, resistor 1. It's the same as the current through this equivalent resistance here, R23, which is the same as the current through circuit element 4. Each of those have a current of 4 amps through them. I'm going to start filling in a couple things in my table down below. So we have a total current of 4 amps. We have 4 amps through our first circuit element and our fourth circuit element. But we don't have 4 amps through resistor 2 and resistor 3. We have 4 amps through those two combined. They're in parallel with each other, and so we have to figure out how does that current split between the two of them. So we're not going to fill that section of the table in yet because it's not 4 amps and 4 amps. So the next thing we can do, though, is because we know that 4 amps of current flows through this resistor here, we could figure out what is the voltage drop across that resistor, that equivalent resistance. We can figure out what is the voltage drop across resistor 2, 3. And that's using Ohm's law. If we know that there's a current, if we know the current and the resistance, a current of 4 amps going through 4 ohms of resistance, there's going to be a 16 volt drop across that equivalent resistance. Let's take a look back here at our circuit in FET. So we have 4 amps of current, and we are going to see that across this 4 ohm equivalent resistance, if there's 4 amps running through it, we're going to have a 16 volt drop across it, which means that if we have 4 amps running into this parallel branch, some of it going to the left, some of it going to the right, we can even see that visually. You can see the current's flowing, and then part of it goes left and part of it goes right. we are going to have 16 volts dropped across each one of these resistors that are in parallel with each other, because we remember elements that are in parallel with each other have the same voltage drop. So it's 16 volts here in its equivalent resistance circuit and 16 volts here in the original circuit. So what we can say is that this V23, the voltage drop across this equivalent voltage, is equal to the voltage across resistor 2. It's equal to the voltage drop across resistor 3, which is 16 volts. So why don't we take that and fill that into the table? There's a voltage drop of 16 volts across resistor 2 and 16 volts dropped across resistor 3. And now we actually have enough information to use Ohm's law to solve for the rest. Remember, Ohm's law is the relationship between voltage, current, and resistance. And so if we know the voltage and the resistance across a resistor, we can figure out the current, or if we know the current and the resistance, we can find the voltage. And so looking at our table, we can see that for each circuit position, 1, 2, 3, and 4, we know either the voltage or the current, as well as the resistance. So we can now use Ohm's law to figure out the missing piece. So step 4 here, solve for everything else. Using Ohm's law. So let's start with the voltage drop across circuit element 1. It's going to be I1R1. There's 4 amps running through this 5 ohms. So we're going to have 20 volts dropped across resistor 1. We don't know what the current through resistor 2 is, but Ohm's law says that I2 is equal to V2 over R2. So we have 16 volts dropped across this 8 ohm resistor. It means that 2 amps are flowing through resistor 2. We're going to see very similarly for the current through resistor 3. It's going to be V3 over R3. 16 volts going across 8 ohms of resistance, also 2 amps. 2 amps and 2 amps. Let's think about that. Oh, well, we had 4 amps coming into this parallel branch, and they are both equivalent. They both were equal resistances, which means that that current was going to split equally down each branch. 2 one way, 2 the other way. That makes sense. And then the last thing is finding the voltage drop across resistor 4. So it's going to be I4R4. It's 4 amps running through 6 ohms, which is 24 volts. So let's just fill these into the table here. 20 volts dropped across resistor 1, 2 amps through resistor 2, 2 amps through resistor 3, 24 volts across resistor 4. Notice that the totals of the voltages, 20 plus 16 plus 16 plus 24, does not equal 60. But 20 plus 16, the voltage drop across that parallel branch, plus 24, does equal to 60. So remembering that these two guys were in parallel to each other, they had the same voltage drop across them. And then similarly, the current is 4. It's 4, these guys combined, and it's 4 and it's 4. It's 4 everywhere in the circuit, including where we had parallel branches, but that parallel branch was the sum of the two currents in each of the branches. And lastly, just going to fill that back in. We had, let's fill out the rest of this, 15 ohms there. So I just want to double check here back in the circuit, making sure that everything we're seeing is making sense. So we have 4 amps flowing through this whole circuit here, 4 amps. When it gets to this junction, 2 amps goes one way, 2 amps goes the other way, and then combining back together, they combine back to 4 amps, and that continues to flow. So that's all making sense. We see that the voltage drop across this first guy here is 20 volts. We see that the voltage drop across this guy over here, 16 volts. And we see that the voltage drop across this last guy, 24 volts. All those voltage drops combine to 60 volts, the voltage supplied by the battery. Perfect. And then the last thing we're going to do is to figure out what is the power consumed by these circuit elements. To figure out power, you actually have a number of options. So this is our last step here. We're going to figure out the power. You can use voltage times current. You can use voltage squared divided by the resistance, or you could use current squared times resistance. Any of those will work. If you do the math, you'll see that no matter which way you do it, you'll end up with the same value. The easiest one is voltage times current, and so that's what we're going to do. We're going to see that the power consumed by the first resistor is the voltage drop across it times the current through it. It's 20 volts and 4 amps. It's 80 watts, saying that 80 joules of energy is being consumed by that resistor every second. 80 watts. You're going to keep doing all that. I'm not going to repeat this all the way through down to P4, and you're going to end up with 32 watts consumed by resistor 2, 32 watts also consumed by resistor 3, 96 watts consumed by resistor 4. Last thing we also want to do is figure out the total power, and this is the power supplied by the battery. This is going to be the voltage of the battery times the current flowing out of the battery, 60 volts, 4 amps. We end up with 240 watts. 240 watts supplied by the battery. And here is a double check to see if you've done everything correctly. However much power is produced by the battery should be consumed by all of the circuit elements. Whether they're in series or parallel, it doesn't really matter, as long as it's conservation of energy. However much energy is being produced should be consumed. And so what we can do here is we can take these numbers here, 80 plus 32 plus 32 plus 96, and that equals 240 watts. Let's draw an actual W there. And what we can see is that the power supplied equals to the power consumed. There's a good check. We've done this correctly. Okay, let's do one more example, and we'll go through this one a little bit quicker, and let's see how it goes. So this one's slightly more complicated in that we have two of these parallel circuit branches, and in one of them we have two series elements. We have two resistors in series in parallel with another resistor, and that branch is in series with two other parallel elements, and each of those are in series with a single resistor. So it's going to take a little bit of work, but we're going to break this down in a couple of steps until we can get down to our series circuit and then into our single resistor circuit. But from there, all of the same concepts are going to apply. So first thing we're going to do is take resistor 1 and resistor 2, these guys here, and we're going to break them down into a single resistor, or we call that R12. These are in series with each other. So this is going to be 5 plus 7. It has 12 ohms of resistance. Now, what that's going to look like, I'm going to draw this really quickly. That means that we have this is R12, it's 12 ohms. This is R3, it's 4 ohms. This is R4, it's 4 ohms. R5 is 4 ohms. And R6 is 2 ohms. Now, by combining resistors 1 and 2 together, we end up with a little parallel branch. And so to combine those guys together, to figure out what is resistor 1, 2, 3 combined, the combination of resistor 1, 2, and 3, well, it's going to be this 12 ohm resistor combined with the 4 ohm resistor. They're in parallel, so we do the 1 over plus 1 over business, and we end up seeing that this whole section right here offers an equivalent resistance of 3 ohms. So we will draw that in our simplified circuit. We also see here that R45 is going to be 1 over 4 plus 1 over 4 to the negative 1. It's going to be 2 ohms. So redrawing our circuit, we're going to have a 14 volt battery supplying current to resistor 1, 2, 3, which is 3 ohms, and then to resistor 4, 5, which is 2 ohms, and then to resistor 6, which is 2 ohms. And last thing we can do is break this down into its most simple form, a single resistor. The equivalent resistance of this whole circuit is going to be 3 plus 2 plus 2 is 7 ohms. So 7 ohms here. Okay, so now our steps, pretty straightforward. What we're going to do is start with our most simple circuit, and we're going to work our way back through the other circuits, filling out the table as we go, trying to get either the voltage or the current for each of the resistors. And then once we have one piece of information about each resistor, we're able to use Ohm's law and figure out all of the rest of the pieces of information. So let's start with the total current, the current coming out of the battery. That's going to be the voltage supplied by the battery divided by the equivalent resistance of this whole circuit. It's 14 volts to 7 ohms, and we get 2 amps of current. That means that 2 amps of current is coming here, which means 2 amps of current is flowing through here. Right? So this means that the total current is the same as the current through this equivalent resistance 1, 2, 3. It's the same as the current through this equivalent resistance 4, 5, and it's the same as the current through resistor 6. So and now those are all 2 amps. So if we want to, we can say, okay, the total current is 2 amps, and the current through resistor 6 is 2 amps. So we can use Ohm's law to figure out the voltage through resistor 6. We'll do that a little later, but we're still a little stuck for resistors 1, 2, 3, 4, and 5 because we only know the current through the equivalent resistances for each of those. Now, what we're going to do, because we know the current through resistor 4, 5, let's figure out the voltage drop across resistor 4, 5. And that's using Ohm's law. It's going to be the current through 4, 5 times the resistance of 4, 5. It's 2 amps across 2 ohms. And there's a 4 volt drop across equivalent resistor 4, 5, which means that there's 4 volts. If there's 4 volts across this guy, then that means there's 4 volts across each of these guys. I'll show you the circuit really quickly. So here is this equivalent circuit. So there was the circuit that we started with, 5 ohms, 7 ohms, 4 ohms, 4 ohms in parallel with each other, the 2 ohms down here. We broke it down to 12 ohms up here from the 5 and the 7, and then reduced these to 3 ohms, 2 ohms, 2 ohms. We can see that the voltage drop across this guy here is 4 volts, which means the voltage drop across each of these guys here is 4 volts. 4 volts on the left side, 4 volts on the right side. They're in parallel with each other. They have the same voltage drop. Okay, so that means that V45 is the same as the voltage drop across resistor 4. It's the same as the voltage drop across resistor 5. They're both 4 volts. We can fill that into the table. 4 volts and 4 volts. We can, in a step in the future, we will use Ohm's law to figure out the current through there. But let's look at this guy, resistor 1, 2, and 3, and let's use this circuit here in the top left of the screen right now to figure out the voltage drop across it. We know 2 amps goes across the equivalent resistance of 3 ohms. So using Ohm's law, we can figure out the voltage drop across that combined resistance. So V is equal to IR. Oh, sorry. 2 amps across 3 ohms is 6 volts. And so what that means is that the voltage drop across 1, 2, and 3 is the same as, let's be careful here, the voltage drop across this guy is the same as the voltage drop across this guy, resistor 1, 2, and it's the same as the voltage drop across this guy, resistor 3. Let's write that down, then let's quickly peek back at the circuit that we have in the simulation. So it's the same as the voltage drop across resistor 1, 2. It's the same as the voltage drop across resistor 3, which is 6 volts. Okay, so what we saw, 6 volts across that equivalent resistance, which means it's 6 volts across here, which means it's the same as, no matter where we put these leads, it's 6 volts across each of those two guys, the 12 ohm resistance and the 4 ohm resistance. But that is not, okay, you'll see here, that's the same as the voltage drop here, 6 volts across this whole branch. But that's not going to be the voltage drop across each of these individual resistors. It's 2.5 across this first guy, and it's 3.5 across the second guy. Let's see how we can get those numbers, because that's not 6 volts across each of them. It's 6 volts combined across both of them. Okay. But we did figure out that the voltage drop across resistor 3 was 6 volts. So here is what we need to do. If we know that the voltage drop across resistor 1, 2 is 6 volts, then the current through resistor 1, 2, using Ohm's law, is V, the voltage drop across 1, 2, over the equivalent resistance of those guys. It's 6 volts divided by 3 ohms. It's 0.5 amps is going to flow through that top branch. It's saying that up here, 0.5 amps is going to flow, which means that up here, 0.5 amps is going to flow. 2 amps flows here into this junction. We now know that 0.5 amps flows up and around, And then that means that, well, you could probably figure this out then, 1.5 amps is going to flow down here. We'll confirm that using Ohm's law shortly. But knowing that 0.5 amps flows through this top branch, that means 0.5 amps flows through R1 and 0.5 amps flows through R2. And so that means that I12 is equal to the current through resistor 1 is equal to the current through resistor 2, which is 0.5 amps. And filling that into our table, 0.5 and 0.5, we now have one piece of information for the voltage or the current for each of the resistors, and we know the resistance, so we can use Ohm's law to figure out the rest. I will leave that to you to solve. So I'll just tell you that the current times the resistance here, 2.5 volts there. The current times the resistance for resistor 2 is 3.5 volts. The voltage divided by the resistance here is going to be 6 divided by 4 is 1.5, 1, 1, and 4 over here. What was the equivalent? Resistance here was 7. And then the last check that we can do here is to figure out the power that is consumed by each of these circuit elements. We can see if the power consumed by all the elements is the same as the power produced by the battery. So let's just quickly do this. And this is equal to, right, power is just the current times the voltage. So 2.5 times 0.5 is 1.25 watts. 3.5 times 0.5 is 1.75 watts. 6 times 1.5, 9 watts, 4 watts, 4 watts, 8 watts, and 28 watts is produced by the battery. So let's just do our double check here, see if we've done everything correctly. We should get 1.25 plus 1.75 plus 9 plus 4 plus 4 plus 8. Didn't do this math prior, but I'm assuming it's correct. Plus 9 plus 4 plus 4 plus 8, 28 watts. The power supplied equals the power consumed. So that means we've done everything correctly.